was a complete newer, so we have to go back and do a bit more of the stuff that is required. Okay, so paper 5. Give me notes. I'm going to send the notes once more. So what you what we were doing in paper 5. Just give me 1 second. Okay. Just a second. This one. Uh, Last time, TK, you can go through the videos. TK, we're just doing paper 5 introduction, and then we'll go back to doing P4 topics. Starting from physical chemistry. So you had the last thing that we were doing was we were collecting gases. Okay, सारों को screen नजर आ रही है ना? We were collecting gases, and what happened in gases was that you had gas range. Remember, P5 is all about the common sense and doing practicals, planning practicals, analyzing data from practicals, and evaluating the results. So gas range, we did gas range. What were other methods of collecting gases? It was gases could be collected over water. We did that. Here, those were the two main ways of collecting gases. We talked about the apparatus being airtight, especially when you're drawing apparatus. It has to be always airtight when you're collecting gases. Iske andar na, I had to discuss a few things when you're doing an apparatus. The trouble with an airtight apparatus is कि when you start a reaction, you get how to. I mean, the trouble is how to start a reaction, and especially if the apparatus is airtight. For example, if I want to react magnesium with HCl, so what needs to happen? How do we keep the apparatus airtight? So what needs to happen in that case is that let's say I've got a piece of Mg and I have to collect hydrogen gas that's going to be produced. Okay, so let's say this is my apparatus and एक सेकंड इसकी ड्राइंग सही कर लें. अच्छा, so this is my apparatus and there's a tube, a delivery tube. ठीक है, make sure ये जो gas वाली tube होती है, that's known as a delivery tube, and that delivery tube goes to a gas range. So there's this. So there's this gas range over here, and let's say that's our gas range. So I've got acid HCl, and I need to put in Mg in it, right? And the whole idea is that I want to collect. Acha, इसमें ना, remember in P5, you have to pay attention to all the little details, the small details. So you have to collect H2 gas and measure the volume as well. Preferably measure the volume. So I need to put in Mg into HCl. The trouble is that this entire flask is completely stoppered. It's completely airtight. So if I want to put in Mg over here, I would have to open the apparatus up, right? And if I do that, as soon as Mg falls into it, if the apparatus is open, the H2 gas would escape from the top, right? So you can't do this while keeping the apparatus airtight at the same time. I mean, that's the challenge. Because you can't do it this way. You can't throw in Mg from the top. So instead, what you're going to do is, if the apparatus is airtight, what you're going to do is you're going to keep the Mg. Once क्यों गया? तो इस तरह. अच्छा, what you're going to do is you're going to keep the Mg inside in a, let's say, in a small tube. That's where your Mg is. तो ये लिख देते हैं. So you keep Mg in a bottle, in an open bottle, and place it inside the acid. Okay, so it's already there. And then make the apparatus airtight. Now the reaction hasn't started yet. So and then make the apparatus airtight. Now the only thing that needs to be done now is that you're going to tilt the apparatus. So tilt the apparatus because now it's airtight, so that the bottle falls into the acid. Yeah, it falls into the acid. And reaction starts. Okay, so the trouble was you can't really open an airtight apparatus, so you have to ensure at all times that the apparatus is completely closed even at the start of the reaction. Okay. So is this part clear? Hala, is this clear? Baba, Sada,
Yes,
Rumesh, yes.
sir.
So now the next thing is you also have to remember that the first particles of gas that are eventually collected in this gas range, they're not actually going to be hydrogen gas. Because remember, hydrogen gas is going to be produced in the conical flask over here. It's going to take some time to move through the delivery tube, and then it's going to start filling up the syringe at the other side. But what is happening is that there's already going to be air in the delivery tube. There's going to be air over here as well. So since there already is air present, the first thing that's going to be pushed into the gas syringe, it's going to be air. Okay, so and collected initially. Okay, that's what you're going to collect, and then hydrogen gas will reach the gas stage. Okay, will reach the gas stage. So that's one thing. Now there's another thing which is that you have to ensure that at all times the apparatus has a constant temperature. You can ensure that the apparatus always has a constant temperature, especially when you're measuring volume. ठीक है उसका क्या है you don't want so what you don't want is uh, as air expands or gas expands or contracts if the temperature changes. Because you don't want the temperature to change while you're doing the experiment. Okay. So that's one thing. I mean, so you have to take care. I mean, they're going to ask you little stuff. Okay. So moving on to the next thing that we're going to do is this is all about gases. We're going to talk about drying a gas. If you collect a gas, how to dry a gas. So usme what you do is there are a couple of dehydrating agents. Okay, so you're going to use So you're going to use dehydrating agents. A lot of your dehydrating agents are anhydrous salts. For example, you're going to have calcium chloride anhydrous, and it's capable of absorbing water, and it will eventually become hydrated. So, I mean, a lot of your electronic devices, they have these dehydrating agents, which are often used to dehydrate a salt. I mean, to absorb water from a gas. If there's water or there's moisture, that could be done. There's certain other dehydrating agents like concentrated sulfuric acid. So what you can do is you can bubble gas through it. Again, you have to be very careful with the apparatus that you're using. For example, if you have let's say this is a test tube. So drawing is very important. They're going to ask you to draw this. So it's a very simple thing, but people make mistakes with this. So your delivery tubes have to be placed like this. You've got concentrated sulfuric acid over here, and the tube that's where the gas is coming from, it has to be inserted into the concentrated sulfuric acid so it bubbles, and the other one has to be outside it. Okay? So make sure you draw this correctly, especially when you're trying to dehydrate a gas. Or if it's an anhydrous salt, in that case, what you're going to do is you just have to pass the gas over it. Okay, so there's delivery tube. Gas is coming from this side, leaving from the other side. And in the middle, you'll have your anhydrous salts. Here, for example, calcium chloride. And that would absorb all the water molecules. So the gas is passing through it. So, okay, that's about collecting gases. Especially when it comes to collecting gases, there are two more ways of collecting gases. One is downward delivery, and the other one is upward delivery. So downward delivery is for heavy gases, and these gases have a mass that's greater than 29, which is the MR of air, or the average MR of air, वो nitrogen और oxygen दोनों का average है. So downward delivery is pretty simple. You've got so let's say this is your delivery tube, and here's my beaker, and the gas would come in. And because it's a heavy gas, it will fill up the container, and it's not going to leave it because the air particles from the top would be pushing it down. The air would be lighter. These particles are heavier. So any gas that's heavy, that's going to be collected this way. For example, you've got carbon dioxide gas that's 44, got an MR of 44, and that's very heavy. So okay, that's downward delivery, and the other one is exactly the opposite, which is that's the opposite. That's the upward delivery, and that one is for collecting light gases. lighter than 29, which is again air. So what's going to happen is that your beaker would be placed upside down or gas jar or whatever container you're using. And because it's a light gas, all of it is going to be trapped at the top. An example of a light gas is hydrogen gas or helium gas. Okay, so it's going to be collected. Now, the only trouble with downward delivery or upward delivery is that you can't measure the volume of gas. You get that? One second. So you can't measure the volume of. So you can't measure the volume, especially if it's an invisible gas. So you can't really see what the displacement is. I mean, it's going to be completely invisible to you. So if it's completely invisible, there's no way you can actually collect the gas that's going to be present because you can't see it. Okay, so that's for collecting gases. The uh, last thing, I mean, there's a the gases is done. We'll move to we move to measuring colors. Uh, so we're done with gases. So how do you measure the intensity of a color or the absorbance of a color? There's a thing called the colorimeter, and that's used for measuring. Specifically measures absorbance at a particular frequency or wavelength. Now, what it does is that it's a simple device, and let's say there's a colorimeter over here, and let's assume there's a bulb at the other side, or whatever the color of the bulb is. Now, always remember, and let's assume it's the color of the light is white, and there's a solution in the middle. Now, what always happens is that when light passes through a particular solution, let's say this is blue copper sulfate, aqueous, and there's white light that goes into the solution. On the other side, what happens is that white has all frequencies. It's got violet, indigo, blue, green, yellow, orange, and red. So it's got all sorts of frequencies, white light. As soon as it hits the blue colored copper sulfate, basically the reason you see it as blue is that it is emitting blue light. So violet, indigo, blue pass through, whereas green, yellow, orange, they don't. Which means these are the frequencies that have been absorbed by the copper sulfate. So the light that you actually see is the light that is not being absorbed. Okay, so the reason copper sulfate appears to be blue to you is that it's not actually absorbing blue. It's absorbing all the other colors. You don't see red when you see copper sulfate. You don't see orange. You don't see yellow. You don't see all the other colors. But but you see all shades of blue. If it's light blue, then it's probably absorbing the violet light as well, and you're just probably seeing blue. So, so that's known as a complementary color. If something is black in color, that means not black. If something is, let's say, yellow in color, that means yellow is the only light that it's not absorbing, whereas it is absorbing all the other frequencies. I said, so what does the collimeter tell us? The collimeter is going to have an axis which would have absorbance written over there, and on the other axis you're going to have wavelengths or frequencies. So if this appears to be blue, if the collimeter only gets all the violet, indigo, blue colors, frequency क्या होती है? Wavelength. Just a second, let me just Google. Um, the wavelength of so violet is at 380 Newton meters. So let's say this is the extreme end, and that's 380 Newton meter wavelength. While the other one, the other extreme, the red extreme, that's 750. So you've got all sorts of colors in between: violet, indigo, blue, green, yellow, orange, and red, right? This is the visible range. So you see all these frequencies. Now, since you're seeing blue, that means blue is the one that's not being absorbed while the other colors are they're being absorbed. So it would probably look like this, that these colors, the yellow, orange, and red colors or frequencies of wavelengths, these are the ones that are getting absorbed. So the collimeter, they never reach the collimeter. While the collimeter shows all the other, I mean, it shows absorbance at violet, indigo, blue. So all the blue shades, I mean, it's getting those frequencies, but not the other ones. ठीक है, ये वाला part, is this part clear? How a collimeter basically works. Nobody clear, Hala? Mawa, is this clear?
Yes, sir.
Achha, so, and also have this other idea that this absorbance is kind of proportional to concentration. The more copper sulfate you're going to have, the higher the concentration of copper sulfate, the higher the intensity of the blue color. So the absorbance would increase. If it's dilute, if the concentration of copper sulfate is very less, the absorbance would be less as well. You're not going to see enough blue. There's going to be a lighter shade of blue. So keep this in mind that absorbance of a collimeter kind of directly translates into the concentration of the particular substance whose absorbance you're trying to measure. I said, I'm moving to the next thing. So collimeter is just this. I'm going to add. So you see light blue, less absorbance. That would just mean dilutes USO4. And if you see a darker version or more intense blue, that means you have concentrated copper sulfate. You guys will keep this in mind what a collimeter does. So I'm moving on to the next thing about P5 is that you'll be. I'm sorry, we kind of done with the apparatus. Now the next thing is we'll just talk about basic stuff and techniques that are used in the lab. उसके अंदर you've got measuring mass of a substance. So how do we measure the mass of a substance? Normally it's an electronic balance, okay, which has a scale, and that scale gives you It gives you a reading. And whatever substance you're trying to measure, that's probably in a small tube. And you'll and that tube will have that substance in it. Acha, so the name for this thing is called a top band balance. How do we measure the mass and how do we construct the table? Or you did this in practicals as well. So the first thing is you're going to try and measure the mass of this tube. So it's the mass of container plus whatever the substance that you're trying to measure. That's the first measurement you're going to make. Then what you're going to do is you're going to take this substance and use it somewhere. So you take this and maybe use it in a reaction. So यहाँ पे ना let's say there's a beaker which has some, let's assume we've got an acid and you've poured it into the solution and you've done a reaction. So now the container would be empty, except okay, there would be some residue that would be still left over here. So the next reading that you're going to take is it's going to be the mass of container plus residual whatever substance you're trying to measure. So that's the second reading that you're going to take. Okay, you have to add the word residual because there's going to be some stuff that would be still sticking to the container. And then you're going to take the difference, and that will give you the exact mass that went into this container over here. So the last thing is that's the mass of Fa used slash grams. Okay, so these three readings would all be there, and the mass of Fa used, that's going to be the difference of the above two values. And keep this in mind when you're taking the difference, the error in each value the errors will add up. So if and the error is the smallest graduation divided by 2. Whatever that is, you have different top end balances, they have different accuracies. So if I have this that it's let's say this is 3.25 plus minus the error is the smallest graduation divided by 2. Then this would be, let's say this one is 3.10 plus minus smallest graduation divided by 2. Let's say this is 3.10 plus minus 0.005 grams. Now the final value, the error would be 3.25 minus 3.1. That's going to give me 0.15. The error would add up and it's going to be 0.01 grams now. Okay, so make sure when you take the difference of two values, the errors, they all add up. Ye clear hai? Hala, is this clear?
Yes, sir.
So again, that's basic stuff. The next thing is like really, really important, and that's how do you make a solution? You're going to be asked very often. The first one is how to make a solution. The next one is how to dilute a solution. But for example, I'm being asked to make a solution. and the volume of the solution is 250 cm cube, and the concentration of the solution is 0.01 mole per dm cube. I'm being asked to prepare this solution. Okay, that's the amount I'm being asked to do. So solution concept, I'm trying to make a solution of NaOH. Now the first thing I told you was that in the lab, for the sake of accuracy, you can keep this in mind. For percentage error or for lowering percentage error, always large amounts of volumes are used. Because your percentage error is what it's the error in a measurement divided by the value, whatever value, whether you're measuring volume or whether you're measuring the mass or the concentration times 100, right? Well, you can't really improve the error much. I mean, you can use a burette, you can have accurate devices, you can obviously improve the error. But if you keep the value as big as possible, if the quantity that you're trying to measure is as big as possible, the percentage error would automatically decrease. Okay, it's the denominator, it will automatically start, it will start to decrease. So so you always make solutions in larger amounts first. And I'm going to tell you why. For example, if I want to make NaOH, right? So how many moles of NaOH is this? Just to make this specific solution, the trouble is, what is the mass of NaOH that is needed? So moles is what? Moles is concentration times volume. If I do that, it's 0.25 in dm cube times 0.01. So if I do this math on my calculator, it's going to be, yeah, 0.25 times 0.01. That's 0.25 times 0.25 times 0.01. So that gives me 0.0025 moles. And if I convert that into mass, which is moles multiplied by the MR, MR is case में, what I'm going to get is it's 0.0025 multiplied by the MR, which is of NaOH, it's 40. So it's going to 40 karo. What do we get? We get 0.1 grams. Now the trouble is that 0.1 gram is too small a quantity. It's very hard. 0.1 gram is like really tiny. So it's very small. So we've got an issue, which is that it's the percentage error is going to be very high. Imagine you're going on a top band balance, and you're trying to measure a very tiny quantity of NaOH. That's impossible. This is the amount of NaOH that is required to make this solution. Okay? So the trouble is you don't actually make this solution. What you do is, and you don't go and make a solution with 0.1 gram of NaOH. What you do is you multiply it by 10, or you use a larger quantity. So instead of measuring 0.1 grams of NaOH, to improve the accuracy or to reduce the percentage error, I'm not even going to measure 1 gram, I'm going to measure 10 grams. Well, 10 grams is is 100 times more. Because I'm going to measure a much bigger quantity, and I'm therefore going to prepare a solution that's going to be 100 times more concentrated. Yeah, so basically what I'm doing is I'm having 100 times more NaOH, and the solution being prepared is 100 times more concentrated. What's 100 times? That's one more per dm cube. So that is 1 mole per decimeter cube. So यहाँ तक ये idea clear है कि why we are not using small quantities, even if they're asking us to make a solution that has a very low concentration. Is that clear? ये part clear, उमर clear है? हाला,
जी
मामा is
सर।
there. तो आपने क्या करना है? आपने वो low concentration और small quantities में जाना. You're going to make a much higher concentrated solution, and then later on, what you're going to do is you're going to dilute it. Okay, so you're going to dilute it, and that will. So पहले तो ये वाला कर लेते हैं 100 times more. I'm going to make one more per dm cube. So every time in the lab, what is normally done is that they always prepare a solution with a much higher concentration, because they can always go to the lower concentration by dilution, by adding water to it. So pehले the steps. How do we prepare a solution? So first thing is measure 10 grams accurately. We had this tube which we were trying to measure. अच्छा, इसमें ना there is, so there is 10 grams over here. The next thing is, remember I'm trying to make a 250 cm cube solution. The next thing is I'm going to use a beaker, and you remember the original challenge was that I had to prepare a 250 cm cube solution, but instead what I'm going to do is I'm going to take that 10 gram and I'm going to put it in some distilled water. Let's assume that's 100 cm cube distilled water, approximately. The reason for doing that is we want to dissolve it first. So I'm not going to add a lot of water to it. I will have a stirrer. Again, this is, remember, you're going to use a glass stirrer. So I'm going to try and dissolve it. It's easier to stir in a beaker, so that's what we're going to do. Once that has happened, I'm going to then transfer all the solution into a volumetric flask. So your volumetric flask is the long, it's the long cylindrical. So your volumetric flask has just one mark, which is a two. I mean, it comes in many sizes. We'll have a 250 cm cube mark, and you would obviously need a separating funnel. And you'll fill this up till the mark. You're going to add more distilled water to it. So that's how we're going to write down the steps as well. Okay, they'll ask this question very frequently. Uh, the next thing I'm going to do later on, so he measured 10 grams of NaOH. He placed it in a small beaker. used a glass stirrer and started stirring until all the enema is dissolved. Once it has dissolved, he transfers it to a volumetric flask where he fills it up with distilled water. Okay, so and when he's trying to transfer to volumetric flask, you're going to add the washings as well. So wash with distilled water and add the washings as well. Because you don't want anything sticking over here. You don't want anything on the separating funnel as well. So when you're using a distilled water, you're also simultaneously washing the separating funnel. You're going to wash the beaker and throw the washing into the conical whatever volumetric flask over here. So transfer to volumetric flask, wash with distilled water and add the washings. See, other things, you get big questions on this. So add तो इसको लिख लेंगे directly. अच्छा, but the trouble is we are trying to make not a 0.01 mole per dm cube solution. We're actually making a solution that's 100 times more concentrated. After this, there's going to be another step where you're going to dilute this solution by adding even more water to it. Okay, we'll discuss that in tomorrow's class. ठीक है? चलिए ठीक है, everyone. We'll continue with the same thing. Tomorrow ये clear है ना? इसमें कोई question नहीं किसी का? Okay.